we go. So, starting over. I'm excited to introduce Ashley Rao this morning. She's going to be presenting case studies from Leers Weinzapfel Associates in Boston. They're award-winning mass timber projects. We have the John Olver Building in UMass Amherst and the University of Arkansas Stadium Drive residence halls. So we've had a number of events this year focusing on mass timber, and it's just a really exciting way to close the year, still promoting really fantastic projects. And I also wanted to note that Ashley has served as on the jury for PA Coat and done a number of really wonderful things. And I hope that this presentation is a segue for continuing to have an open dialogue and supporting each other in all of our sustainable efforts. And so without further ado, I'll hand it over to Ashley to dive into her presentation. Thank you all for joining us today.
Thank you so much for having me today. I'm really, I love Philadelphia. I worked in Philadelphia a lot in my early years, and my husband is a Philly boy. So this is really a pleasure to be here virtually on so many fronts too. Thank you. I was also going to say this is an intimately sized group, so I would just encourage you all to interrupt me as I go if you have questions or comments. Let's keep this conversational because there's no reason to be bored first thing in the morning. We should save that for later on when you're drinking something other than coffee. All right, let me share my screen and I'll just jump in. Okay. Hopefully you are all seeing a single slide that says mass timber in practice. Okay, great. You can just never tell. Super. So first I wanted to introduce myself. Danielle gave a little bit of background. I'm Ashley Rao. I'm an associate principal with Leers Weinzapfel Associates of Boston, Massachusetts. This is us. We are about a 30-person firm. We're woman-founded, and we are 67% women, 40% ethnic minorities. And one thing that we've done recently that was really, I think, awesome for us as a practice is get just certified by the ILFI. You may be familiar with it. It's kind of through like the LBC process, but it's a transparency measure that really kind of helps you be transparent about what you're good at and also transparent about what you're bad at and kind of improve yourself and think about those measures that contribute to a sustainable and equitable practice as well. Our areas of focus are really kind of four: academic work, infrastructure work. You may recognize this infrastructure plant from the West Philadelphia side of the Schuylkill there at U10, civic work and community work. And increasingly also mass timber projects is an area of focus that we're really proud of. I may be preaching to the choir here, but I wanted to go through a brief introduction of why wood, why it matters and what it kind of does for all of us. You are probably very familiar with this slide, but we know that between building operations and building construction, that the building sector is responsible for 40% of our overall energy use. And the embodied energy piece of that is 11%. Embodied energy, when we talk about embodied energy, we're talking about all of the energy that goes into the extraction, processing, transportation, construction, and disposal of the materials that we use every day in our buildings. We have, I'm sure this is background knowledge for this group too, but when we talk about the carbon emissions of a typical high-performance commercial building, the energy use itself is the operations, which over the lifespan of the building is about 60% of the building's energy use. But the embodied energy, the energy in the materials and construction is about 40% of that overall energy. And I think when you look at these kind of separated out, it tells one story. But when you really overlay them over time, this is why we need to focus on embodied energy now. Because in these now 8 years before 2030, really 80% of the energy in a building is embodied energy. Only 20% of that is operational energy. So right now in this kind of critical time frame where we still have the ability to change the course of overall global warming, we're really talking about embodied energy in new construction that's going to make the biggest impact. And just kind of in broad numbers, looking at three of the most common building materials, concrete, steel, and wood, we know that wood has the lowest embodied energy of those. Steel is 3 times as much, concrete is 5 times as much. So what does that mean, embodied energy? Where does the carbon go? How does it get there? This is a diagram, not my diagram, but one that kind of takes you back to almost 3rd grade, you know, when you learn about transpiration and respiration and what trees do and how they're the kind of opposite of human beings. But that's when trees basically absorb and use carbon dioxide, that is stored in their kind of own bodies. And up to 40% of that is in the trunks and the branches. So when we harvest that timber and sustainably replant that timber, 40% of that carbon is really sequestered and taken out of the atmosphere. I recently taught a really fun studio class where I went with students kind of and followed the entire process of a tree becoming mass timber. And I'm going to take you on a little snippet through that. So you start out with trees in the forest, harvesting them. The next step is the embodied energy of extraction, processing, transportation, construction, disposal that we talked about. But in the case of wood, it's pretty light. It's debarking this tree. And then cutting it into kind of standard 2x or other, dimensional lumber. There are a lot of different mass timber products. Cross-laminated timber, or CLT, is the one that I'm going to be focusing on today. Glulam has been around forever. Nail laminated timber, dowel laminated timber, LVLs, LSLs, parallel strand lumber, mass plywood panels. There's a lot of different products out there, and they're actually changing. I added 2 from the last time that I gave this actual same talk too. So this is an area that's developing, and there's some really amazing industrial processes that are looking for more ways to use smaller lumber more effectively. So today I'm really going to be focusing on the opportunities in cross-laminated timber and floor panels and in shear walls. Sorry, I just lost my mouse here. Excuse me. So cross-laminated timber, you probably all know, but this is essentially a process where 2x are laminated together in different layers, kind of facing opposite directions. And what's unique about that is it can really span in 2 directions as opposed to kind of your typical glulam or other lumber, which has a one-way span. This is like a brief look at the fabrication process of CLT. So I'm taking you here into the factory. One of the first steps, again, is there's like almost the standard manufacturing size in North America is 80 by 40, which is largely based on the size of a truck, can then transport it. But those pieces of 2x, 2x6s, 2x4s are glued together. And you can kind of see each of those layers here. And then this is the resultant CLT panel. And then there's really the possibility of using digital manufacturing, digital processing to mill that and really to customize the shapes and really prefabricate a lot of this. So you're seeing here the Hundegger. This is a 6-axis CNC machine. This can do everything from simple cuts to really complex joints, which is hugely exciting because it kind of translates what you might have learned in middle school in your shop class, or if you're a carpenter at home, it's the same tools, but it's being applied on a huge scale and through a digitized process with incredible precision. So this is kind of almost a cartoon of the kind of complexity of joints that you can create through this digitally processed mass timber. Something that combines all different shapes of wood, steel plates in between them. It can be used to create complex geometry, such as the Art Gallery of Ontario. Mass timber can be used in large span structures. And this is the Olympic Oval from British Columbia. And it can be used increasingly in tall buildings. Another example from the West Coast, this is Rock Commons, which is, I think, the tallest mass timber structure in North America at this point. I think it's 18 stories. And then just to briefly go, one thing that we face a lot as we are talking about mass timber is, the fears about mass timber, the fears of wood rots. And that's true, But we know how, and we know how to protect it. 600 years ago, that meant that we were really pulling wood structures back and protecting them with huge overhanging roofs. Today, that might mean, excuse me, I'm a little bit behind. Today, that might mean that we're encasing that wood inside of glass and making sure that it's never directly exposed to the elements. The fears are also that wood is, unpredictable or untested. And that's a lot of this is changing with the new code changes. But that's really just not true anymore. This is an example of actually in Japan. You can see this little tiny person here in the corner. Let me see if I can get my mouse out here. This is a full-size mock-up of a 6-story wood building that's being tested on a shake table for seismic. And I think because of the lightweightness of wood compared to other forms of construction, you can really build these full-scale mock-ups and test it, not just the teeny sample of it, but full size in the laboratory on a shake table. The fears are also that wood burns, which is true, but we know how. And one thing that's really interesting about this is I think the way the code really calculates this idea of a char layer. So we know the rate that wood burns, but over the course of it burning, it develops this protective char layer, which actually almost compare to like roasting a marshmallow. You kind of get this outside char, but on the inside, the marshmallow is still there. And the same thing is true for wood. So when you size a wood member, you're really sizing it for that protective char layer that's a sacrificial layer. And then the kind of structural layer is there on the inside. And again, there's a lot of testing going on that looks at and confirms the rate of wood burn and kind of how that performs. This was this is a one of these iconic slides that just kind of shows that one of the key differences between wood structure and steel structure is that steel fails spectacularly, whereas wood burns slowly in a really controlled fashion. So this is something I think from like the late 1800s, just showing like these are the steel I-beams. They're like loose little noodles draped over the remaining pithy core of this wood beam too. So just kind of inverting some of the things that we have been taught to believe about steel and concrete versus wood structure. So from here, I wanted to go and really look at some of our work, starting out with the John W. Olver Design Building at the University of Massachusetts in Amherst. And this project, I am so proud to say was a national AIA COAT winner. Kind of going through that process was a huge education for me and for our entire practice. This building really brings together three different departments at the University of Massachusetts Amherst: architecture, landscape architecture, and construction technology, and creates kind of a new home for them and harnesses really all of their goals. The building is originally designed as kind of a courtyard style building, knowing that is an effective use of kind of exterior materials. It's just the form of that makes sense. And then in the middle, it really creates this common space that brings the three departments together. And what you're seeing here is a section 3D model of it, showing this the shared common space below, which really communicates through skylights up to a planted roof garden above. So this really kind of combines the architecture, the landscape architecture, and the construction technology. This is a view from that central atrium space, which really shows how we try to use and celebrate wood structure kind of in every element here. So you're seeing big glulam beams above, a zipper truss system that really kind of holds that up for that long span. And then right in front of you also is a CLT stair that really communicates across all 3 stories of the building. This is the kind of basic diagram of the building. You're seeing here on the left the overall courtyard form, and on the right some of the key elements of the building. A copper anodized aluminum wrapper, cross-laminated timber roof deck, post and glulam timber post and beam structure, and a composite CLT plus other things floor structure that I'll talk a little bit more about. This building was actually also able to use CLT as the shear wall cores, and over that a concrete foundation. I think one thing we found in our own work, well, I will say, our own work is not totally pure. We're not building all wood buildings, but I think we're trying to really be thoughtful about the use of materials and minimize the use of concrete or steel to where they are performing in a way that wood cannot. To focus a little bit more on that, the rooftop courtyard and the commons assembly above that, just to kind of unpack each of those layers. You see the intensive green roof that was developed together with the landscape architecture department. And it's really used actually almost as a field classroom for study and in planting. And that's over a cross-laminated timber panel roof with cast and plate concrete topping on top of it. That's supported by a glulam beam and perforated metal connector, a composite steel and glulam zipper truss, and then the mass timber structure below. I wanted to take you through a couple of images of just like what this looked like overall in the construction process too. One thing that we found is that mass timber ends up being an incredibly like clean and quiet site, which is important when you're building in denser urban settings, where essentially you see there's the laydown of material here, but that kind of pound you might get of steel or of concrete, riveting or welding. This is really, you've got a couple of cranes and you're just dropping things into place. On the right-hand side here too, this was kind of an early study that we had done of the embodied carbon impact of the structure as well too, using just a really fast tool that's available through Woodworks, their kind of carbon estimator or carbon calculator. A couple more shots from construction here. I'm just seeing all that forming up. And that's the CLT floor slabs and roof and the glulam kind of post and beam structure supporting that. From another angle. And then just kind of getting up close here where you're seeing the glulam post and beam, CLT floors, and the CLT shear walls beyond. So this was, for any code geeks out there, this was, in an earlier version of the code. We didn't have the advantage of the 2021 code for this one. But so one thing that we had to do was basically to use a variance process to allow, especially for the vertical, for the shear cores. And the local fire marshal was very supportive of that. Looking a little bit more at the glulam beam to column connection, you see that steel collar is really used kind of at the top of the beams just to support the next one. On the left-hand side here, this shows kind of a more clunky set of connections that you might see in some traditional buildings. What we're really focusing on here is using the wood to protect the steel, and use this kind of male-female slip hanger, so that all of the, it's first of all very easy to do. You basically are just dropping that into place, and second of all, that way the wood itself protects that steel connection. Again, the cross bracing and lateral bracing was provided by diagonals and the CLT shear wall cores. And I think this is really where you see some of the power of the prefabrication as well. So all of these pieces came to site, pre-wrapped, prefabricated. And you're seeing here the placement of some of that lateral bracing, some of those diagonal beams, just by a small crew. This is one crane, guy in the crane, and two guys, they're up there on the deck. And there they go. They're putting the pin in there. Again, like a really fast and really quiet construction process with incredible precision of prefabrication. Looking more at those CLT shear walls, we use that for lateral and for the stair and elevator cores. So you can kind of see the elevator core coming together here in the inside of that. So one thing that we were really looking forward to here was to be able to express and experience that wood inside the stair cores itself. That was one thing we worked with carefully on the fire marshal, because we wanted to make these needed to be 2-hour rated cores. And there were some concerns about exposing wood within that system. But what we ultimately did was develop a system where there were 4 layers of gyp on the exterior side of the core. So that essentially maintained the fire rating there. And we were able to expose the wood on the interior of the core. So you kind of get inside and you're like, oh, it's a beautiful, beautiful little woody surprise. Looking a little bit more closely at the floor panels here. So you're seeing, again, a crane lifting an 8 by 40 foot CLT, it's a 5-ply CLT floor panel into place. And you see on top these kind of lines of something. So one thing that this is like a little detail of that. We had worked carefully with the materials research that was happening at UMass. And one thing that they were looking at was actually kind of a composite system that combined CLT slab together with a layer of insulation, a perforated metal connector, and a concrete topping to basically increase the base span that CLT could accommodate. And this was important in some of the studio spaces where we needed, a more open span. This is it was amazing to be able to work directly with the university and put some of their research into practice on this project. The CLT roof deck. And then looking a little bit more at the zipper truss, which is really the main kind of visual feature of this atrium space. And it's also the one that really actually brings together the work that's happening in the building too. So this kind of highlights some of the challenge of this. So this is a model of the zipper truss. This is a trapezoidal space that supports, dense planting, soil load weight, snow load up above. And we also wanted, this visual penetration between the three. Here's the reflected ceiling plan, seeing that trapezoidal shape. So we worked together, and this is really kind of a back and forth between architecture and structural engineering to design, I'll go back one slide actually if I can, to design this zipper truss, which basically uses wood members largely in compression, and then uses light steel members in tension all the way down there. So this is something that's really a three-dimensional solution, and that combines steel together with really expressing wood in unusual ways. And you might say, oh, well, this is like a hugely expensive custom fabrication. But one thing we did was really think about the cost impact of this too, and look towards as many off-the-shelf parts. So really, after working together with the structural engineer a lot, there were very few cast pieces. So you're seeing basically a single cast piece that's the connector, and then we're really able to use off-the-shelf components in terms of all the attachments to really make this a cost-effective and structurally effective system. Just one look at the connector, and then to kind of take you back out. So this is the final realization of that central common space with the skylights coming down through the wood truss, the CLT stair on the side. And that ends up being, such an important and amazing visual connector for all the different levels. One thing that was initially a concern of the university is saying, oh, how are we going to protect the wood? Like, are students going to write on it, like sign their names on it? And one thing that I think we found is that doesn't really happen. People do want to reach out and touch the wood. They want to smell the wood, actually. There's a great, I think when they moved into the building, one of the best feedback we got is like this doesn't have that new car smell. This actually smells like a forest. So there's like, the wood has a bigger impact than I think you'd even imagine. But people are really protective of it. And even though you can reach out and touch these trusses, there hasn't been any problem with students or anyone damaging them. This is a look at the studio spaces here. So this is, again, where we're really expressing that post and beam system of the glue lamps, the CLT roof deck above. And one thing that I think this highlights too is a couple of issues in architecture that you can definitely ignore if you're putting acoustic ceiling tiles everywhere, but you can't if you're trying to expose structure and really, effectively make that a visual part of the experience here too. So you see some of the careful coordination between electrical conduit that's serving the lighting up above. Look at those sprinkler pipes. I think there's some interesting challenges of exposed structure that this really opens up and makes you focus on that RCP a little bit more. This is just a look again on the ground floor, the views out back to the commons, but this is the digital fabrication lab where they actually do on-site testing of, among other things, some wood structures and composites. And even in the offices and in smaller rooms, we tried as much as possible to expose that CLT deck as the ceiling, which has a couple of benefits. It reduces finishes, it reduces costs, and it brings that kind of biophilic nature of wood structure as part of every single space. And that's true in the kind of ground level cafe as well. And this is just a view up of the roof deck above. So that skylight you're seeing kind of penetrates through to the atrium space below. And just kind of the depth and density of planting that this supports. I wanted to go back, I'd earlier introduced this as, oh, this is the structural system. But kind of quick confession is that this building was actually originally designed in steel. And we were about 25% through DD when one of the members of the steering committee at UMass Amherst said, well, couldn't this be in wood? And I think really a huge part of the success of the building, the kind of collaboration between architect and owner, was that everyone said, well, maybe it could be, and took a pause then and really studied it. But so on the left hand here, you're seeing the original steel structure. On the right hand, you're seeing the mass timber structure. But the fact that we were at 25% DD kind of in both systems in parallel allowed us to do some really interesting testing and evaluation of what was the embodied carbon impact of this. This isn't then just it's not just a theoretical, what if this building were in steel versus what if it were in wood. We actually had documents for both of those systems at a pretty good level of detail. So we, together with Woodworks, actually, we used this as a test case. There was a whole building LCA that basically looked at, again, you were probably very familiar with this, but the first time I saw this kind of LCA diagram, I was like, what am I looking at? But this is basically just showing what the boundary is of the life cycle assessment. So this included from the product stage, raw material supply, transport, manufacturing, from the construction process stage. So this is really the building on site, the transport, the construction installation process, use, maintenance, repair, replacement, operational energy, and operational water. And then also some of the end of life stage, what this would take to demolish or deconstruct this, waste processing and disposal. So all of that energy was considered as part of this life cycle assessment. And these are the results. You see the baseline building, which in this case, again, is not theoretical. This is from the 25% DD documents versus the mass timber structure. And I think the key thing to focus on here is just the global warming potential. So the kilograms of carbon. This is a 13% reduction by going to mass timber without making huge other changes in terms of that. So this was for us like a really important and really validating study, and one that we were excited to participate with Woodworks and with Athena at the national level to look at this and understand what this really means. I would also just a warning about life cycle assessments and embodied carbon. This is from Athena's white paper. But thinking about an LCA, you kind of have to have both of these. Like, what are you comparing this to? Because the results represent a range and not an absolute. So we have a really hard time kind of saying, okay, how many tons of carbon per square foot is this building? It's much, I think, more accurate to consider it as a what is the reduction and compared to what? And then finally, just a plug for the COAT Top 10 Super Spreadsheet, which it's an incredible tool provided by national level COAT AIA. And it kind of helps you think about how you establish a baseline for embodied energy, what you're talking about, and how that might differ on building type. So I think for all of these, this is just a way to kind of frame our own heads saying, okay, I'm not necessarily aiming for like 42, pounds of carbon per square foot, but I'm trying to think about, okay, if this is an educational building, what might a low embodied carbon look like? What might a high embodied carbon? How can I kind of help shift that conversation towards lower embodied carbon? And then finally, the embodied carbon story here was just part of a much bigger story of huge efforts to think about embodied carbon, operational carbon, long-term maintenance and durability on this project. So we really highlighted in our COAT application the embodied carbon piece of it, but operational carbon was a huge part of it, the dialogue and conversation as well. And this project ended up being, it was 2 points away from LEED Platinum, but a LEED Gold project. The next project I wanted to look at was Adohi Hall at the University of Arkansas. So it was a new 700, oops, there are 8 questions in the chat. Oh my gosh, I'm so sorry. Let me take one pause real quick and see if there's 9. Okay. Let me take 1 minute and just see if there's any questions here on that. All right. Oh, super. So the CLT, that was actually, so one question is about where does the CLT come from? So for the UMass project, this was Nordique CLT, which is Quebec, or basically kind of upper Canada. It was interesting because one thing, and I'll talk about this more here too, we always are looking for local fabrication. How close can we source this to site? And the CLT,
be good.
the CLT market is changing a lot, but at this point, the Nordique was really the closest location that we could get CLT in the United States. There was also a question if we had looked at nail laminated timber. We have looked at nail laminated timber on a lot of different projects. It's interesting because one kind of downside of nail laminated timber is some of that digital processing and fabrication that I talked about earlier. If you have ever tried to put a piece of reclaimed wood through a bandsaw, you know the problems of kind of combining nails and machining. So you lose some of the ability to shape and prefabricate that, but there really can be huge cost savings because essentially they're just like 2x6s, 2x8s, nailed together. When it's being used in a slab, that can be a really cost-effective way to approach it. We don't have a built project with nail laminated timber, but I promise you, if you invite me back in a year, I might have one to show. So let me keep on going to Adobe Hall, but also I would say please keep the questions coming, and I'll try and stay on top of seeing them too. So this was a new 718 bed student residence hall. And some of the challenges here, sorry, let me get my mouse going again. Okay. So to kind of take you back to the beginning, the little blue shape over here to the left is the location of the new residence hall. The blue square to the right is actual main campus. So this is a project at a remove from campus. It was in the middle of this whole athletic valley of huge stadia and baseball fields. But also you can kind of see this woodland trail, this Oak Ridge trail that kind of winds all the way from the Arboretum through the center of campus and down the hill. So our goal was really to make this part of the site part of that woodland trail, to re-green and reforest this piece kind of from the inside and the out, and connect it to some of the natural resources and beauty of the area. This is a look at the overall site plan. So you can see here the building is, like I said, it's largely a student residence hall, but the ground floor is really animated by a wide variety of student resources. So on the left here in Building B, there are fabrication classrooms. This is meant to be a live-learn community for students that were especially interested in the arts. So fabrication classrooms, seminar rooms, music practice rooms, a music recording room, a performance space. In the middle in Building C was the cabin, the kind of main student social resources. And then Building A, you see, is really kind of the entry to the entire building there at number 4. And that kind of, and then the module of the student residences. Up above, we really, again, you can kind of see that relentless module of the residences, and we also tried to break that up and create social spaces that were at the ends of the building, were at the major points of circulation by the elevator and social stair. This project used, again, a glulam post and beam frame and CLT floor slabs and roof slabs. And again, and this is just kind of that same Woodworks overall carbon estimator, which is a great early way to just check and say, okay, if I'm using mass timber, if I'm using wood structure, how do I think about this, and how do I explain this to owners or to clients? It's equivalent to 937 cars off the road for a year. This was a brief animation we put together, which kind of really looks at that structure. So you can see, again, the glulam frame. You can see the CLT floor slabs and roof slabs You can also see here some places where we were bringing in steel at strategic locations. So at the longer spans underneath the bridges, we were using steel there to help support those. And also in this building, the stair cores and elevator cores were cast in place concrete. And that really was due to two factors. Number one, in this case, we had a really conservative fire marshal who said, absolutely, over my dead body, are you going to build a shaft out of anything other than concrete? And the other one was actually, we ended up putting some of the mechanical units. So the overall ERV for the building on top of that elevator shaft, that causes a lot of vibration. And one thing that wood kind of is a little bit, wood does transmit vibration more easily than other building materials. So we were able to use that strategically to help minimize vibration impact for the overall building by balancing it on top of the concrete elevator core. Here's a brief tour through the building as we move kind of from north to south. So as you're approaching from campus, you enter first into a stand of basically preserved trees of white oak grove. And you can kind of see how the typical student residence floors are lifted up above the ground floor to create a continuous passage from north to south. Here you're kind of moving there underneath these breezeway, these bridges up above. And we also we were using, in this case, this was Bender Holt's CLT. We had really hoped to be able to use locally fabricated CLT, but the market wasn't there yet. So this is actually European CLT. I, again, kind of think about it like the banana versus the spring green. So slow boat transportation is still relatively carbon effective, even if you're bringing that from a long distance away. But anyway, so Vanderholt CLT, but we also tried to use Arkansas cypress, so essentially local finish wood where we could, to again, just make the wood as visible as possible and to supplement with local, native local materials whenever we could. Moving here into that central courtyard space, you're seeing the cabin right beyond. And as I said, this is the central social space of the entire complex. We have exposed CLT roof planks there. We have glulam beams, and again, a glulam queen truss here that again uses steel strategically to support a longer span and a green roof up above.
Just gonna jump in here and say that we have just a couple of minutes left before.
Oh, sure. Okay. No, absolutely. Just to take you through here in the cabin, and then moving you down the stairs. This is through the performance space, that kind of inside-outside connection, and down into some of the workshop spaces to the south. One thing that was really interesting on this project is, number one, we worked really hard to keep that exposed CLT floor on the ceiling, and really, again, be really thoughtful about coordination with mechanical and electrical. The other one here is on the right-hand side, you're seeing into the workshops. We were able to repurpose the CLT skids, which are actually used as almost like a transport mechanism for the CLT, and use that on site to create custom tables and furniture. To zoom on through, again, a key challenge here was the cost. So one thing that we did is we kept wood and steel on the table through schematic designs, that we were able to really show how to use that effectively and understand what, if any, cost premium there was. Looking at the module was, I think, one of the critical pieces here, and a really modular student building. So this shows 2 student rooms and kind of how that lays out into a bay, and how we were able to think about that in terms of using the 8x40 a CLT panel so that everything was used as effectively as possible. I'm going to zoom through here. We talked a little bit before about our local fire marshal, but I think, again, making sure that we're able to translate, okay, this is the baseline steel frame building type 2A, and then this is what the building looks like in advanced timber building in type 3B. Non-combustible exterior walls, but unprotected and combustible frame. And then one thing I also just wanted to highlight here were a couple of challenges that we found actually during the design assist and fabrication process. One of my takeaways in this project is, when you size a steel beam, your W12 is a W12 forever and ever. Our basis design was a Douglas fir glulam, 14 1/4 inches by 18 inches. But when we ended up selecting our mass timber supplier, this was Binderholtz spruce pine fir. It's a different tree. It has different inherent strengths, as well as an overlay of a European versus a North American kind of set of structural standards. So some of those beams got a lot deeper, which was a problem, specifically in some of these toilet room locations. But I think that for me, that was a real learning process here. And then just also a quick look at going back to that nail laminated timber question. This was a huge effort to coordinate the penetrations with all of those bathrooms in the semi-suites. So what you're seeing here is all of the pre-drilled penetrations that were factory fabricated. Each green dot represents that. And each red dot actually represents a pre-drilled screw hole for the crane lift to put that into place. There were 4,116 of those. Our contractor called this the Swiss cheese slab, but it represented huge savings in the field. Just a couple of construction shots here. And then the last thing to highlight was just, again, we actually had some challenges with the field tolerances of the concrete. So we had to work together and actually back off of that prefabrication in one key location where the timber met that concrete core so that we could really size that on site and address each of those individual field conditions for that construction tolerance. Just a few more images, and this was ultimately the goal, was that even in kind of a modular room, that every room had direct visual access to the amazing Ozark Hills beyond, and also a piece of that exposed CLT wood structure that was really visible and part of every student's experience. So this is just the construction process, but I will stop here. Thank you all so much for having me today. If you have any questions, please jump in while you still have a few seconds left.
Absolutely. And I would actually suggest that if you want to send any additional questions to our email, AI@phillycoat, we're more than happy to help facilitate the connection and help answer those additional questions. But thank you so much, Ashley, for being here today. This is really insightful and motivating. It's always kind of far off to see projects like this, but to see it happening on a regular basis in such a feasible way is incredibly motivating and something we want to help promote. Thank you again.
Me too. Thank you so much for having me.
Great. And for everyone else on the call, I did want to, I don't know if anyone attended AIA Forum this year, but COAT hosted an event that highlighted the Amy Gutman Hall in Philadelphia. It's a 6-story mass timber building. And Gensler provided a study during that presentation, which we're working to try to make a little bit more public, but they provided a study that actually encouraged the feasibility of mass timber from a cost neutral perspective. It was a little bit of sort of design build efforts on their end to make that happen. It's such a new project type in Philadelphia, but that's exciting to see in contrast to most contractors that we're working with in Philadelphia saying that there's a cost add for this type of construction. Just a little tidbit there for everybody. Awesome. All right, well, without further ado, we're gonna dive into our subcommittee updates. And like I said, if you have any questions for Ashley, please reach out to AIA@phillycoat@gmail.com. And I'll help facilitate that.